So we can send you this recording later. So let's get started. So today we have Introduction to Residential HVAC Systems with Russ King. My name's Ital Torres and I'm with 3C Ren. And before we get started, I just wanted to run through some slides to let you know about who 3C Ren is if you're not familiar with who we are. Next slide. So I know by now most of you are probably very familiar with Zoom, but we ask that everyone make sure that they are on mute throughout the duration of the course. If you would like to verbally participate, please raise your hand in the participant section and we will call on you to unmute yourself, and we encourage you to participate and ask questions through the chat box as well. Next slide, please. A few words about who we are. We are the Tri-County Regional Energy Network. We are a collaborative partnership between San Luis Obispo, Santa Barbara, and Ventura counties, working to improve energy efficiency in our region by offering free programs and services for building professionals and households. 3C Ren is funded by ratepayer dollars, which are collected through the Public Goods Charge Fund on our utility bills. We currently have 3 programs. Next slide, please. That being the first one, the Energy Code Connect program, which serves building professionals by offering Title 24 support for everyone from plans examiners and inspectors to architects and contractors. Within the Energy Code Connect program, we offer Energy Code Coach service and over the phone, online, in the field support for Title 24 related questions for both residential and non-residential projects, and trainings similar to this one, but more code oriented. Next slide, please. Another program we offer is our building performance training program, which serves building professionals such as architects, engineers, contractors, and real estate professionals by offering technical and soft skills training related to building science principles, high performance buildings, marketing, and communication techniques. Next slide, please. And our last program is our home energy savings program, which incentivizes contractors to helps residents save money and make their homes healthier with energy efficient upgrades through incentives and rebates. With that, I'll pass it over to Russ to get us started with today. Thank you so much.
Awesome. Thanks, Itzel. We appreciate it. Well, good morning, everyone. Nice to have you here with us this morning. We have about 2 hours to cover a very deep topic. We have a lot of slides to go through, but I think we'll be just fine. These slides, by the way, are based on a book that I wrote a few years ago called HVAC 1.0 Introduction to Residential HVAC Systems. I do not own the rights to that book anymore. I sold that company to CalCerts. CalCerts now owns that book, but they let me teach classes based on the book. And it's available through Amazon if you want to purchase it. So check it out. I actually wrote that book back when I was training a lot of HERS raters because that was back when there was a lot of funding for retraining people from different trades and different backgrounds and professions. And there was no good book that was really basic, super basic on HVAC. If you went online or you went to a library and you looked up a book on HVAC, it talked about how to hook up wires, how to charge refrigerant, how to do all this stuff. And that's not what these people were looking for. They wanted to know, what is this thing called? How does this work? What does this do? What is it when somebody says this? So I like to call this book is HVAC for people who will work around HVAC, but not work on HVAC. So that's kind of what we're going to talk about today, is a very basic introduction to residential HVAC systems. that someone like a homeowner would really be interested in, who's just about to invest a ton of money into their HVAC system, or maybe is looking into completely redesigning it, or perhaps architects, perhaps building department folks, utility people, rent employees, things like that, who need to know about what we're talking about when we say things like coil, condenser, and duct leakage, and TYs and register boots and stuff like that. So that's kind of what we're going to talk about today. So it's intended for people with little or no practical experience with residential HVAC systems, and it's intended to put you on a level playing field with people who know a lot about HVAC, or at least think they do. It's kind of amazing to me how HVAC contractors will go into someone's house and just like use all these fancy terms, all this jargon and stuff, and try to kind of intimidate the homeowner with these all these fancy words and everything. And it turns out they don't really know as much as they think they do, and they start saying things. So I like to say that uh, this training kind of helps fine tune your BS meter, if you know what I mean. So what we're going to talk about today is how to identify different types of HVAC systems and the distribution systems. How is that heating and cooling ducted to the house? We'll talk about some terminology. We'll talk about understanding airflow. Airflow is fairly intuitive. If you think about air flowing through a duct, you kind of have a fairly good idea what it's supposed to do. But there's some things that you may not think about. So we'll talk about some of that, understanding airflow. We'll talk about comfort issues, what affects comfort. We'll talk about some design strategies, how to go about designing a heating and cooling system. And then we'll talk about things that affect efficiency. So there's two really important parts of a heating and cooling system. The first one is comfort. That's making our house comfortable. But then the second one is doing it in a way that doesn't use a lot of energy. We want to accomplish the comfort by using as little energy as possible. So those two things in some ways go against each other, but in other ways they go hand in hand. So we'll talk about those. So let's start really, really basic. So BTU, you've heard the term BTU, British Thermal Unit. It's how we measure heat energy. And in its most basic level, heat is really just vibration of molecules, okay, and atoms. So they're just vibrating, and that gives off what we feel is heat, okay? But we have to measure that somehow. And we measure it in British thermal units. I don't know why we haven't come up with our own thermal units, but we use British thermal units. So you'll hear the term BTU. And just to sort of quantify that, one BTU, one British thermal unit, is about the same amount of heat that's stored in a wooden kitchen match. So if you take a regular wooden match, you light it, you strike it, light it, you let it burn all the way down to the nub, you've just released 1 BTU of heat into the air. Okay. And then we have to measure heat flow. And we do that in BTUs per hour. So when you talk about a house losing heat or a house gaining heat, we say it loses X BTUs per hour. And if it helps, think of them as kitchen matches. So if this house has a heating load of 30,000 BTUs, that means it loses 30,000 BTUs per hour, or it loses 30,000 kitchen matches worth of heat in 1 hour. And in order to keep the house warm, we have to replace that heat. So we have to put 30,000 kitchen matches per hour back into the house. And that's our equipment. That's our capacity of our equipment. Okay. So BTUs. When we heat a house, we're adding BTUs to that house. And when we cool a house, we're removing BTUs. That's very important to understand. Cooling is the process of removing BTUs. You don't put coldness into the house, okay? You remove BTUs or you dilute the BTUs, okay? And when we dilute BTUs, we change the temperature. So we don't put coldness into a house, we remove BTUs. An air conditioner removes BTUs and a heater adds BTUs, okay? The rate at which a home loses or gains heat can be calculated. It can be estimated. So we say, at what temperature do we want to estimate it at? So that's the outdoor temperature. And then the indoor temperature is what the comfort temperature that we want the house to be, like our thermostat setting. And we look at the difference between those two temperatures, the indoor and the outdoor temperature. We call that the delta T. The difference between those temperature is what drives heat out of the house in the wintertime or into the house in the summertime. Okay. And that can be calculated, that can be estimated. If you can calculate the area of a building's envelope and the type of envelope and the delta T, you can calculate how many BTUs per hour are coming into the house, and you can calculate how many BTUs are coming out of the house. And we call those the loads on the house, the heating and cooling loads, or load calculations. Okay. So to maintain a constant temperature inside the house, that comfortable temperature that we want the house to be, which, by the way, in California is specified by code, and that is 68 degrees in the winter. That seems kind of cold. Most people like their house warmer than 68, but that is the code determined temperature at which we calculate our loads at. Whatever they set the temperature to, that's fine. They can set it higher if they want to. Okay, but that's the temperature that we calculate the loads at. And then the outdoor temperature, we look it up in a table based on the city that the house is located in. Okay. But to maintain a constant temperature inside the house, whatever that temperature is, 68 in the winter, oh no, by the way, it's 75 in the summer. To maintain those two temperatures, we have to constantly add heat in the winter to replace the heat that's being lost. So if we can calculate the load, how much heat is being lost in the winter, we can pick a heater that will replace that heat at the same rate, BTUs per hour, in order to maintain a constant temperature. Okay. And that amount of heat that's coming from the heater, or the amount of heat that can be removed by the air conditioner, we call that capacity. So load is what the house needs. Capacity is what the house gives us. Think of it as supply and demand. Okay. The demand is the load. That's what the house needs. And the supply is the capacity. That's what the equipment gives us in order to meet that load. And the ability to size that is very important. Okay. It's very important. That's you can certainly have equipment that's too small and won't keep up. But a lot of people don't realize you can very easily have equipment that's too big and causes all kinds of other problems. Okay, we'll talk a little bit about that. Another term that you'll hear is a ton of cooling. Well, how much does a ton of cooling weigh? It doesn't weigh anything. It has nothing to do with weight. It's an old archaic term that goes way back to the days of when they used to buy ice to keep things cold before there was any kind of mechanical refrigeration. Um, in fact, here I'm based in the Sacramento area, and there's a train museum here. And one of the things they talk about a lot is they used to send trains up to Lake Truckee and Lake Tahoe, and they would cut. They had places up there where they cut these huge blocks of ice out of the frozen lakes and put them in these train cars filled with hay and bring them down here so that the farmers and the butchers and everyone can keep their stuff cold. And so they would buy the ice in tons. They would say, I need to buy 5 tons of ice for my vegetables. And so they buy ice in tons. Okay. And then when they invented mechanical refrigeration, they would say, this unit right here can cool as much as 5 tons of ice. And so they called it a 5-ton air conditioner or a 5-ton refrigerator. Okay. So as it turns out, a ton of ice can provide about 12,000 BTUs per hour of cooling. So that's what a ton is. When they manufacture an air conditioner, they test it and they try to get it as close as they can to increments of 12,000 or 6,000 for half tons, and then they label it. Okay, so the tons, by the way, is a nominal capacity. It's what we call it. We call it a 5 ton, but that doesn't mean that it's going to give you exactly 60,000 BTUs of cooling. Okay, we'll talk about that. So a ton is roughly 12,000 BTUs per hour of cooling. The typical residential HVAC systems come in the following increments. Okay, and this is changing a little bit with mini splits and some other things, but this is fairly typical, and this has been very typical for many years. So 1.5 tons, 2 tons, 2.5 tons, 3 tons, 3.5 tons, 4 tons, and 5 tons. And I never quite got a good answer as to why they don't make a 4.5 ton system. Very, very few manufacturers make a 4.5 ton system, but that's it. Okay. So if you take the number of tons and you multiply it times 12,000, that'll give you an approximate amount of cooling that piece of equipment will provide you. So for example, a 2-ton air conditioner will give you 12,000 times 2 or 24,000 BTUs per hour. Okay. A 3.5-ton will give you about 42,000 BTUs per hour of cooling, and so on. Okay. Unfortunately, it's not that simple. Air conditioners work by moving BTUs from one place to another, and their ability to do that has a lot to do with the temperature in those two locations, from where it's moving from to where it's moving to, that delta T that it has to move. It's kind of like pumping water up a hill. Okay. It's taking heat from a lower temperature inside the house, which is 75 degrees, and it's moving it to the outside of the house, which is actually hotter. It's moving heat in the opposite direction that it wants to go. And the bigger that distance is, it's like it's like having to pump water farther uphill. Okay. And so if you take the exact same pump and you pump at a certain height, it might move 22 gallons per minute. But if you take that exact same pump and you have to pump it higher, it might only move 18 gallons per minute. Okay. But it's the same pump. It's the same exact pump. So that's our air conditioner. We call it a 2-ton air conditioner, but if it has to cool in a certain location, it'll give you a certain amount of cooling. But if it has to cool in a more extreme location, it won't give you as much cooling. All right. We call that the design capacity. The tons is the nominal capacity. That's just what we call it, a 2-ton system. The design capacity, we have to figure that out. And it's affected by a whole bunch of different things. Okay, so here we have an air conditioner, a 2-ton nominal air conditioner that has to pump heat from 75 degrees all the way up to 110 degrees outside. That's a big difference. Okay, what is that, a delta T of 25, 35 degree delta T? That's pretty substantial. In doing that, it will move 22,500 BTUs, not quite 24,000, right? It's a 2-ton air conditioner, so you would say 24,000, but because it's having to pump heat so far up a delta T, it's not giving us quite 24,000. But if you're doing it in a much milder location, say on the coast where the outdoor temperature is only 85, and you're pumping it from 75 up to 85, that's only a delta T of 10. Then it'll actually give you more than 24,000, 24,500. Okay. So it's very important to realize that the actual cooling capacity, the design cooling capacity, depends on design conditions, especially the outdoor temperature. All right. Oops, I forgot there was some little circles and stuff in there. Okay. So how do you know what size air conditioner? If someone says, "Hey, what size air conditioner do you have on your house?" You can actually figure it out. Okay. It's not super difficult. Um, you go outside and you look for a number that's increments of 12 or 6. 6 is the half tons. Okay. So one and a half times 12 is 18. 2 times 12 is 24. 2.5 times 12 is 30. So these numbers indicate the tonnage of the equipment, and they're going to be in the model number of your condenser, your outdoor unit. Okay. And the older style ones. Okay. The newer ones, and manufacturers are making life so complicated these days. Now they have like a 19 and a 25 and a 31 and a 37, and it's like they're just trying to say, well, ours puts out a little bit of extra, but it's just their way of discerning their old style from their new style and stuff like that. It's kind of crazy, but anyways, if you're careful and if you have a little bit of experience doing it, or if you have an older unit, this works fine. Okay. And by older unit, I mean something that looks kind of like this. All right. This is an older air conditioner or heat pump condenser. It sits outside. And if you look on the side of it, there's going to be this little sticker, this little permanent sticker on here. We call that the manufacturer's nameplate. Okay. And if you zoom in on that, you'll see model number. And then if you dissect this model number and look for, let me go back a couple slides, one of these numbers, and sometimes they're preceded by a 0, by the way. So 048, 024, 030, 036, and so on. Okay. And if we look in here, we see, oh, look, I see an 048 right there. So this is a 4-ton condenser. Okay. 4-ton condenser. So that's how you can go out and look at a piece of equipment or look at a model number and kind of figure out. Like I said, some manufacturers are making it more complicated these days, especially some of the mini splits and stuff like that. By the way, mini splits can go down to half a ton and three-quarters of a ton. The old style condensers only went down to 1.5 ton, and a 1.5 ton is way too big for a typical ADU, accessory dwelling unit, which are super popular these days. That's why the mini splits are so important for ADUs and things like that, is because the tonnage is much smaller and it matches the load of a very small dwelling unit, and you don't oversize it like we used to with the 1.5 ton. We used to, that was the smallest we can get. Put a 1.5 ton on a 600 square foot ADU, and it's like you could hang meat in that thing, and it's not very efficient. Okay, all right. Here's another one. GSX GSX 030 or GSX 13. So you're like, what is that 13? But here you see an 030. So that would be a 2.5 ton. Here's another one. TCGF 36 S41. So you got to kind of just, pick out the important numbers, and they try to confuse you, but this would be a 3 ton. Okay. And sometimes if you can get your hands on the manufacturer's literature, there'll be a little decoder ring that'll show which numbers are the tonnage in there, and that will help you too. Okay. So pretty straightforward. Pretty straightforward. Also be aware that air conditioning coils, that's the indoor unit. Well, we'll talk about that if you don't know what a coil is. And sometimes the air handlers, we'll talk about that. A furnace is an air handler, for example, will also be rated in tons. Okay. So you've went out and you looked at your model number of your condenser and you say, oh, that's an 036. That's a 3 ton. I got a 3 ton condenser. And then someone might say, well, how big is your coil? How big is your furnace? And you say, okay, you go look at the coil. You can do the same thing on the coil, the indoor unit, use the same thing and say, oh, it's also a 3 ton coil, which is fairly common. They're usually matched, but not always. Your coil can be bigger than your condenser. You can have a 3 ton coil and a 3.5 ton condenser. Or sorry, I said that backwards. The condenser, the outdoor unit, the indoor unit can be bigger than the outdoor unit in terms of tonnage. So because it gives you better airflow and things like that. We'll talk about that. We'll talk about the condenser defines the nominal tonnage. So when they say, how big is your air conditioner in your house? Well, your air conditioner includes a condenser, a coil, and an air handler. It's the condenser is what we name it by. So if your condenser is 4 ton, or sorry, if you got a 4 ton coil and it's a 3 ton condenser, and someone says, how big is your air conditioning system? It's a 3 ton because of the condenser. The condenser limits how much cooling you can put out. Having an oversized coil allows you to squeeze a little bit of extra capacity out of it, but it's mainly to improve airflow. The bigger coil lets more air pass through it, so you get better flow into your ductwork and things like that. That's usually why they upsize a coil. Also for efficiency. Speaking of efficiency, we rate air conditioners with two numbers called the seasonal energy efficiency ratio and the plain old energy efficiency ratio. They've just come out with some new ones, and so you will see the SEER2 and EER2. All right. 2 just means the new version of it. Okay. It's tested differently. You do not want to compare an SEER to an SEER2. It's a different test. Okay. But equipment manufactured after a certain date, they've started doing these new tests. And so when you see the rating on them, they'll say SEER2 and EER2. Okay. They're just numbers that come from laboratory testing of the equipment. They hook it up, they blow air through it, they measure the BTUs and how much electricity it consumes, and they rate it. Okay. And you can look these up. And the EER and the SEER depends on the condenser coil match. Okay, that changes the efficiency as well as the air handler, how much air is blowing through it too. Okay, but you can look all that stuff up. You can Google it, and it's the AHRI directory is what it's called. So, as implied by the extra word seasonal, the SEER rating is the efficiency of the equipment over a season. So it takes into account variations in temperature and things like that, whereas the EER does not. SER ratings are always higher than EER ratings for any particular given piece of equipment, but there's no simple formula to convert one to the other. I'm actually not 100% sure why they use both. It has to do with energy modeling. So when you run an energy model, it wants to know the SEER and it wants to know the EER, and it uses those two to estimate energy use. Okay, and now it's the SEER2 and EER2. Um, so you're usually going to be asked for two numbers, the SER and the EER. There, the ER is usually or is almost always lower than the SER, but there's no fixed relationship to them. Approximately the SER times 0.875, but not always. Not always. Never compare the SEER from one piece of equipment to the EER of another piece of equipment. Two very different numbers. And don't compare the SEER to a SEER2. Two different test procedures. Okay. Both numbers represent efficiency in sense of the output divided by the input. So you're getting out cooling, the removal of heat, and you're putting in electricity. Okay. So it's what you get out for what you put in. And obviously, higher is better. Higher efficiency is better. They represent how many BTUs an air conditioner will remove for each unit of electricity that's put in watts per hour. Okay. It's an efficiency number. The efficiency and capacity are two very different things. Capacity is how much cooling a piece of equipment will give you, and that's capacity. Efficiency is how much electricity it takes to do that. So you get 5 tons, 4 tons, 3 tons. That's the capacity. But you can have a high efficiency 3-ton and a low efficiency 3-ton. They both give you 3 tons of cooling. It's just the high efficiency uses less electricity to do it. Okay. So just like a car, you go to the auto dealership and you can mix and match your car. You can pick the engine. Do I want a 4-cylinder? Do I want a 6-cylinder? Do I want an 8-cylinder? What kind of transmission do I want? I want stick. Do I want paddle shifting? Do I want automatic? And then you can pick the body style. Do I want a really sleek car or do I want a big boxy van? Okay, you can pick all those things, and depending on what you pick, it's going to affect the miles per gallon. So the same thing happens with air conditioners. You pick your condenser, you pick your coil, and you pick your air handler. Okay. All of those things together has an impact on your SEER and your EER. Manufacturers have to test this and publish it in order to have what we call a rated combination. That means a condenser coil air handler that was tested together so that we can document and prove that it's the efficiency that we claim. It has to be tested and published by AHRI. So when you look up AHRI, you're going to look for condenser. You're going to find the condenser you want. You're going to find the coil with the coil that you want, and then with the air handler that you want. And that'll give you the rated efficiency for that piece of equipment. So it matters. It matters. The same condenser with a different coil will give you a slightly different efficiency rating. All right. AFUE. This is an efficiency rating, but it's for gas furnaces. It stands for annual fuel utilization efficiency. And it's actually a fairly simple number to understand. It's also output, what we're getting, divided by what we put in. Okay. Higher is better. AFU efficiency ratings for gas furnaces. And what we're putting in is gas, and what we're getting out is heat, BTUs per hour. We're putting in gas. A unit of gas, natural gas or propane, has a certain amount of BTUs in it. And if we could put that many BTUs in and get that many BTUs out, it would be 100% efficient. But they're not. The old furnaces were like 72% efficient. You'd put in 100 units of gas and you'd get out 72 units of heat. So it was a 72% efficient furnaces. Well, they've gotten much, much better. They're getting pretty darn close to 100%. There's furnaces out there that are rated at 96%. Okay. Low 90s is more common. High 80s for many years. Usually when it goes from 80 to 90, you go to what's called a condensing furnace. A condensing furnace just squeezes some extra heat out of the exhaust. And when it does that, the exhaust condenses moisture. It's cooling the exhaust. There's a lot of moisture in the combustion products that come off of the flame. There's a lot of moisture in there. And when you cool it, it condenses. So we call it a condensing furnace. But it also pulls a lot of extra heat out of that exhaust gas. So instead of blowing 180-degree fumes out of your roof, it cools that down and uses that heat, puts it back into the airstream. That's a condensing furnace that greatly improves the efficiency, but it also makes it a little bit more complicated piece of equipment. And you have to find a place for that condensate liquid water to go too. So you gotta be aware of that stuff. Because gas has a fixed amount of BTUs in it, the AFUE equation can be very, very simple. BTUs out divided by the amount of BTUs in. The small number out divided by the big number in. If they were the same, it would be 100% efficient. But it's not 100% efficient, so it's a little less than that. So the BTUs coming out is a smaller number than the number you're dividing it by. So it's going to be a fraction like 0.96, 0.92, 0.90, 0.80, things like that. So an AFU of 80% means that you get 80 BTUs of heat for every 100 BTUs of gas that you put in. Most furnaces will list the input and the output right on the nameplate, and you can calculate the AFUE. It's very simple. You take the AFUE, to get the AFUE, to calculate the AFUE, you take the output, the smaller number, divided by the input, the bigger number, and you'll get a fraction like 0.8, 0.9, 0.92, 0.96. And then you multiply it times 100 to get rid of the decimal, and that's your AFUE. Okay, very simple. Here's an example. Here's the input, 75,000. Here's the output, 60,000. So you take the small number divided by the big number, okay, times 100. You get 0.8 times 100 is 80. Okay, 60 divided by 75,000 is an AFU of 80. So for every 75,000 BTUs you're putting in, you're getting out 60. Not that great. That's an old furnace. Okay, older. Here's one. Output is 57, input is 60. You're putting in 60, you're getting out 57. So you take the small number divided by the big number, 0.95 times 100, 95. That's a 95% efficient. Much better. Much, much better. Definitely a condensing furnace. Okay. All right, next one. This is an important one these days. HSPF. This is the efficiency rating of a heater called a heat pump. Okay. And we'll talk a little bit more about heat pumps, but it's basically, in its most simplified description, is an air conditioner that runs backwards in the wintertime. All right. In the summertime, an air conditioner captures heat from a cool house and dumps it out to a hot air. In the wintertime, it takes heat from the cold outside air and dumps it into a warm house. And its efficiency, its ability to do that, and how much electricity it takes to do that is rated in a number called HSPF, which stands for Heating Seasonal Performance Factor. Okay. And again, it's an output divided by input kind of thing, but we're talking BTUs and electricity, so it's not as intuitive as the AFUE, which is BTUs to BTUs. But it's pretty easy to understand, and it's easy to compare. So you can look at this heat pump's got an 8.8, this one's got a 9.4, and it's 9.4 is better. Okay, so but it's not as easy. It's like air conditioners. You got to go look in a table to find it. On furnaces, you can just look right at the furnace and see what it is on the nameplate. All right, here's another terminology that we're going to talk about: CFM, cubic feet per minute. It's cubic feet per minute. It's how we measure airflow. It's how we quantify airflow. It's used in a lot of different areas related to HVAC. Okay. The following are common airflows that we use CFM to describe them. Airflow through ducts. Okay. You're blowing air through ducts and you got air going to a room. We quantify that in CFM. How much air is coming out of the register, out of the supply register in your ceiling? That's CFM. How much air is blowing across the air conditioner coil? That's the indoor unit. That's what's cooling the air. Okay. How much air is passing through that coil? We measure that in CFM. Duct leakage. How much air is escaping from the ducts? We quantify that in CFM. And then we convert that to a percent. So we say your ducts leak 30%. If your system's moving 1,000 CFM, 30% of 1,000 is 300. So if you have 30% leakage and you're moving 1,000 CFM, that means your ducts are leaking 300 CFM. And by the way, They did a big study a few years back, and that was the average leakage of existing homes in California, 30%. 30%. Okay. Air leakage into or out of your house. So infiltration is measured in CFM, and we measure it by pressurizing your house, by blowing air into your house and seeing how much CFM it takes to hold a certain pressure. That's how we measure leakage of air coming out. Okay. And then air just delivered by a fan, just a plain old fan. A blow dryer could be rated in CFMs. Anything, I suppose you could, wave a fan and measure the CFMs for that as well. All right, so CFM, cubic feet per minute. So how do we sort of make that more intuitive? All right, so similar to gallons per minute. Okay, like when you open your faucet, you can measure with a stopwatch in a 5 gallon bucket, divide by 5, and however many minutes, you get gallons per minute. That's pretty straightforward. Air is not so easy to measure. All right. But we're talking about is a volume metric, a volume per time, a volumetric flow rate. And you can actually visualize CFM if you think about it. If you think about it. Okay. So a soap bubble, imagine blowing a soap bubble about 15 inches in diameter. Okay. That's 1 cubic foot, about close to it. 1 cubic foot, 15 inches in diameter, a sphere. All right. Let's just call that a big old bubble. That's just a big old bubble. So if one big old bubble came out of a nozzle every second, so imagine a 15-inch bubble and you got a nozzle and you put soap on it and it blows a bubble, and you get this 15-inch bubble every 1 second. So 1001 pop, 1002 pop, 1003 pop, 1004 pop. Okay. One big bubble per second is 60 big bubbles per minute. That would be 60 CFM. Okay. One big bubble, pop, one big bubble, pop, one big bubble, pop. 60 CFM. What a typical bathroom needs, or what a typical bathroom fan exhausts, is 50 CFM. So it's a little less than that. So imagine the CFM making all that racket in your bathroom, blowing air out. If you're lucky, you're getting 50 CFM. And if you can imagine the air coming out of the top through the roof, one big bubble, pop, one big bubble, pop, one big bubble at about 50, 60 CFM. Okay. So you kind of, if you think about it and you put your hand over a red shirt and imagine big old bubbles coming past your hand. Okay. You can start to approximate CFM. I've I'm out of practice, but I used to be really good. I used to be able to put my hand over a register and be within 20 CFM or so of a register moving 180, 200 CFM. I could get pretty darn close. And then of course we had a flow hood right next to us, and that we would check it, and I just do that over and over and over again. I got pretty good at it. But it's so 60 CFM is one bubble per second. A 5-ton air conditioner moves 2000 CFM. That's hard to imagine that many bubbles. Okay. That's a lot of bubbles. All right. So a typical bedroom is going to move 90 to 120 CFM. So that's 1.5 to 2 big bubbles per second. Okay. So bubble, bubble, pop, bubble, bubble, pop, bubble, bubble, pop, bubble, bubble, pop. Okay. 90 to 120. That's what a bedroom needs. Okay. For air conditioning. A 3-ton will move 1200 BTUs. That's 20 big bubbles per second. I can't count that fast. Pop, pop, pop. Okay. So that's a lot of bubbles. So that's moving a lot of air. Okay. So when you talk about the entire system, that's a lot of bubbles. When you're talking about individual rooms, you can kind of imagine that. You can kind of quantify that. Okay. So try to estimate the airflow by putting your hand over something and imagine how many bubbles are blowing past your hand. 15-inch diameter soap bubbles. Okay. But to be really good at it, you need a tool. And the tool that we use is called a flow hood. And it's got a big scoop on it. You put it over the register and it measures airflow. Okay. There's two kinds. There's a passive flow hood and there's a powered flow hood that's more accurate and things like that. But that's the tool that we use. All right. All right. That's CFM. Convection. Now we're going to talk about heat transfer. Convection is heat moving Um, it's heat moving by some sort of a fluid. There's a fluid carrying that heat with it, and we call that convection. So a fluid is carrying BTUs from one side of the wall to the other side of the wall. That is BTU being transferred by convection. Okay. In houses, it's typically air is the fluid. You can have it through water and other things too, but it's air. So that's leaks. Leaks in our house. If we got warm air escaping from our house to the cold outside, that's carrying BTUs with it. We call that convection, also known as infiltration. Okay. Homes lose and gain a lot of heat by convection, especially older homes. Convection is a very important part of how we heat and cool our homes. All right. Convection is how we get air from the heater to the rooms. We blow air, we blow CFM to the rooms. So, examples of convection: infiltration, drafts. If you got a big window and you put your hand down at the bottom, you feel cold air falling off that window. That's cool air with less heat in it dropping down to the floor, and it's being replaced by warmer air up above. Ceiling fans, that's convection. Ceiling fans cool our body by basically uh, convective heat loss on our skin, and if we sweat, it gets even more. Stratification, hot air rising. Okay, that's a form of convection. And then the whole entire way a central forced air heating and cooling system works is by convection. It heats and cools air, and then it blows air to where it needs to be, to the rooms. That's a form of convection. Conduction. Conduction is heat that passes through a solid object. When you pick up a coffee cup and you feel it's warm, nice and toasty warm. Actually, my coffee's getting cold. But if you feel heat going through that ceramic glass, that's BTUs being conducted through the solid cup. Okay. And in homes, that's heat conducting through our walls, through our ceilings, through our floors, through our windows. That's all conduction. That is improved by improving the R value of the walls. Conduction occurs through any solid material that has a temperature difference across it. In a home, this is usually the conditioned shell, what we call the thermal boundary of the home, which is made up of the floors, the walls, the ceilings, the windows, the doors, all the solid objects, all the solid surfaces that separate the indoor temperature from the outdoor temperature. Some of these conduct more heat than others on a per square foot basis. Okay. Windows. Windows conduct a lot of heat compared to a wall or a ceiling. And that's something that's very visual. You can see it with an infrared camera too. Okay. The next one is radiation. In the wintertime, our houses radiate heat. Okay. And it's a good example of radiation would be a heat lamp. The old heat lamps we used to have in our bathrooms, we had a little twist timer, and it's this hot lamp would come on, you could feel it shining on your head, or the heat lamp shining on the food at the buffet. Okay. That's radiant energy hitting the food and warming it up. Okay. In the wintertime, our houses radiate heat, but it's actually a really, really small number. We don't worry too much about it. Okay. But in the summertime, radiant heat gain is huge. It's one of the biggest sources of heat, and that's the sun shining into our windows of our houses. Okay. It's very, very important form of radiant heat transfer is sunshine. We call those solar gains, right? The main source of radiant heat transfer in a home is solar gains. B2's coming in the house by means of sunlight passing through the windows. Homes can lose heat by radiation, but it's very small. Okay. But you can see it with an infrared camera. If you look at a house on a cold day, the house is nice and toasty warm, and you look at a house, what you're actually seeing is radiant heat energy. Okay. Infrared cameras. Sometimes heat will get from the outside of the house to the inside of the house by all three forms: convection, conduction, and radiation. Okay. So when we do a heat load calculation on our house, we're looking at all convection, conduction, radiation for all the different services. We're adding it all up together to get one number so that we can size our heater. And then we do the same thing in air conditioner, except the heat is coming in instead of escaping. Okay. So heat can come into the house by all three forms of radiation. So the sun shines on the roof, that heats it up, that's radiant. The heat conducts from the roof into the attic, that's conduction. Then the attic air gets hot and starts circulating around, that's convection again. Okay, actually convection for the first time. And then it gets down on top of the hot air gets on top of the insulation of the ceiling and conducts through the attic, that's conduction again. And then it might even leak through can lights and holes in the ceiling, that's convection again. Okay, so all three ways of heat transfer happens. So there's radiation, conduction, radiation, convection, conduction, and if it leaks through the roof again, that's radiation. So all this is going on at any point in time. And it's the ability to count that, to quantify that, is what we call a load calculation so that we can size our equipment. And it doesn't just happen through attics, it happens through walls and windows and floors and everything. Okay, which is why software is so important. So, all right, now let's talk about different types. So that was terminology. If there's any questions, by the way, if you have any questions as we go, feel free to type them into the chat, and if I can. And it's so if you see a question pops up in the chat and I'm not paying attention, feel free to interrupt me. But I'll try to keep an eye on it. All right, so we've talked about terminology. So we know what a BTU is. We know what CFM is. We know about efficiency ratings. We know about the three forms of heat transfer. Okay. Now let's actually talk about HVAC equipment. Okay. There are many different kinds of HVAC systems, how we heat and how we cool our house. One of the main ones for residential is split and package. You'll hear that term a lot. Oh, I have a split 5-ton split on my house. I have a 5-ton package unit. I have a 4-ton package unit. Okay. These are configurations of the heating and cooling components. A central forced air heating and cooling system has three components. I mentioned this already. It has an air handler, that's what moves the air. It has a cooling unit, that's the condenser and coil combined, and then it has a heating unit. If it's a furnace, the furnace and the air handler are the same thing. If it's a heat pump, the heater and the condenser and coil are the same thing, and you have a separate air handler. Okay, we'll talk about that. A cooling unit is usually just a condenser, the outdoor unit, and then an evaporator coil. We just call it the coil inside. And it's where, for an air conditioner, the coil absorbs heat from the air and sends it out to the condenser where it dumps it outside. And it does that by compressing and expanding refrigerant. Talk a little bit about that. So let's say altogether, there are four parts. There's the condenser, coil, the air handler, and the heating unit. Okay. Sometimes the heating unit is the air handler, and sometimes the heating unit is the coil. But four basic parts. Okay. How those four parts are arranged is what determines whether it's a split or package unit. We haven't even talked about ducts yet. Okay. So this is a typical split system. And the reason they call it a split system is because the condenser is outside the house and the coil is inside the house, be in the garage, in the attic, inside conditioned space, whatever. Okay. But they're separate from each other. They're far apart from each other. And they're connected by two refrigerant lines. One's about as big as your thumb, and one's about as big as your pinky. Two refrigerant lines, and they run together. And one is insulated, and one is not. Okay. But that's what connects the condenser and the coil. And that's how the air conditioner is extracting heat from the inside air, it's sending that heat to the outside condenser, which is then dumping it out to the outside. An installer contractor can pick or choose different sizes based on the load calculations, based on the brand that they like to use, and things like that. If it's a gas furnace, the heating unit is going to be inside the furnace. So here's our air handler. The air handler is the box that moves the air through the ductwork. The most common version of that is a furnace. Most people know what a furnace is. The furnace has a big fan in it, and that fan pushes air through the duct. So that is the air handler. But a furnace is also the heater. Inside that same box is a combustion chamber, a heat exchanger where flames are happening and air is blowing across that heat exchanger to heat the air. That's our heating unit. So this would be a furnace. Okay. I can't remember if I don't think I have a diagram of a heat pump, but a heat pump, this goes away. This heating unit goes away. This box is just a fan. And then this coil can cool the air like an air conditioner, but a heat pump runs backwards in the wintertime, so it can actually heat the air. Okay. So same same four components, they're just kind of arranged differently, but it's still what we're talking about, a split versus package. Okay. So the fact that the condenser and the coil are far apart from each other, so you can have a split gas AC and you can have a split heat pump, and they look very similar. You can also have package units. Oh, let's see. Oh, by the way, the air handler um, can be upflow, the air blows up, or it can be downflow, the air blows down, or it can be horizontal, the air blows horizontal. And like that's pretty typical in attics. We'll see some more of those. A package unit has all four components in one box. And because the box includes the condenser and the condenser has to be outside, it's everything's gonna be outside with the condenser. So it's a package unit, a package unit. So you got a fan, the air handler, you've got a coil, and you got a heating unit. Okay. So you can have a packaged furnace, packaged gas furnace, they call it a gas pack. Okay. Or it can be a packaged heat pump too. But that's usually going to sit on your roof with your ducts coming out the bottom, or it's going to sit on the floor. And if it's a raised floor house with a crawl space, the conditioner can sit on the ground, not the floor, the ground outside, and the ducts will go under the crawl space. Okay. But it's a package unit. So you'll see both of those. If you drive down 99 through all those little Central Valley towns and you look off in the neighborhoods, you'll see tons of package units on the roofs. Old package units. They're kind of getting out of style these days. You don't see nearly as many. So split system, the condenser coils apart from each other. Package unit, it's all one box. Pretty straightforward. Pretty straightforward. You also hear the term DX. DX. That stands for direct expansion, and that's just how we cool the air. That's a very common. It's probably the most common form of air conditioning we have. It requires some sort of refrigerant that expands and is compressed. Direct expansion that absorbs heat, and so that's how we cool the house. So you can have a system called a split DX, and you can have a package DX. That's just what DX stands for, direct expansion. The other kinds of air that aren't very common would be like a evaporative cooler, a swamp cooler. There are some other types. There's actually a propane and ammonia air conditioners, but direct expansion is the most common type. When you think of air conditioning, you usually you're thinking of direct expansion. All right, let's talk a little about heat pumps. Um, there are different kinds of heat pumps. There's heat pumps that get their heat from the air, and there's get heat pumps that get their heat from water or from the ground. Okay. And when you bury your pipes in the ground to get heat, there's water in the ground. So they also call that a hydronic heat pump or a geothermal heat pump. Unlike common air source heat pumps, it exchanges heat with the ground or water. Okay. They're very efficient, but quite expensive and expensive to install because instead of just setting a condenser outside that's going to exchange heat with the air, you got to bury a bunch of pipes in the ground. So you have to dig very extensive trenches or you have to dig a very deep straight hole to put it in. Okay. But it's very efficient because the ground is a great source of heat, which sounds weird. You don't think of the ground as being warm, but everything has heat in it. Everything, even a block of ice has heat in it. And the ground is always a relatively warm temperature um, compared to ice, let's say. Okay, so there is a lot of BTUs in the ground to be extracted, and so it can be quite efficient. PTAC, package terminal air conditioner, PTAC. That's your basic through the wall unit. Okay, technically a window air conditioner, that's a PTAC. Let's see. Here's a good example. Hotels. Hotels have these all the time. So here's the outside of the building. Here's the inside of the building where the chair is here. You got this little unit with the button on it, and it blows air right on your bed when you're sleeping in your hotel. Sometimes these are under a window on by the front door, and you'll see water running across the sidewalk. And these, I guess, I go to a lot of cheap hotels. Or it could be on a hotel. It'll be under the window, your exterior window. Um, so, anyways, PTAC. It's all one unit. Your condenser is on the outside. Your evaporator's on the inside. Warmish air comes in, it gets cooled off, and hot air comes in and gets even hotter. Okay, the BTUs are dumped into it, so it's extracting BTUs from the inside of the house and putting them outside. It's cooling the house. They make these in heat pumps too, so they can actually reverse and heat the house as well, or the room, I should say. Evaporative coolers, swamp coolers, not super common, but basically they work by water evaporating and it cools. So if you've ever gotten out of a swimming pool on a hot day, your skin feels cold because the water is evaporating. So using that principle, we can cool air and blow it into a house. The problem is that air is going to be very moist. So evaporative coolers, sometimes called swamp coolers, um, they are very popular in very, very dry climates like Palm Springs, Palm Desert, Las Vegas. You see a lot of evaporative coolers because they take very, very dry air, they cool it very well, and they blow it into the house. But when they cool it, it adds moisture. So you want to add moisture to in a humid climate like Florida. You first of all, it wouldn't cool the air very much, but secondly, the air coming in your house would be so humid your house would turn into a green grass monster. So, anyways, um, swamp coolers. Okay, here's what it looks like. There's water dripping through a pad. It pulls air through that pad that cools the air, and then it blows it down inside the house. Very simple, very basic, quite efficient, quite efficient. But again, they're only good in really, really dry climates. All right, gas furnaces. All gas furnaces create BTUs by burning gas, by creating a flame, by taking natural gas, igniting it, and getting those BTUs out of that gas, whether it's piped in as natural gas or in a tank on site as propane. Furnaces burn gas, but they give off potentially dangerous gases. Okay. The combustion of gas results in carbon monoxide, which is poisonous. So you have to be very careful with it. The outer surface of the heat exchanger. So this combustion happens inside a heat exchanger. You don't want the flame to mix with the air that's passing through your house. That's what people die from. Okay. But the combustion is supposed to happen inside a sealed, separate combustion chamber. A lot of times it's just a pipe and they're shooting flame through this pipe and then they're blowing air across the top of this pipe, which is warming the air. But sometimes those heat exchangers crack over time, which is why carbon monoxide detectors are so important. You cannot get a permit for anything, including replacing your toilet. You cannot get a permit unless part of that work includes installing a CO detector, carbon monoxide detector in your house. That's how important it is. Okay. So these gases must never escape into the house air, the air that we breathe. So it goes through this little heat exchanger and then it gets piped out through the roof. Okay. Um, this is one of the main disadvantages of gas heat over electric heat is that it's dangerous. It's dangerous. And not to mention the gas that's coming into your house is explosive. Could potentially blow up. So we're piping explosive gas into our house. We're using it, and that's creating poisonous gas. And we're hoping everything's good. All right. It's amazing we've survived this long. If you get trained with combustion safety, like through BPI, it's kind of scary. It's kind of scary. It's a real eye opener. All right. Central furnaces, these are furnaces attached to a ducted distribution system. So the furnace is in a central location, it's heating air and it's blowing that air out to the rooms where it needs to go. And they're split and there's package, but they can both be central. But you can also have wall furnaces and floor furnaces. Those are not central furnaces. A central furnace is ducted. And ducted central forced air heating systems are the most common you're going to see in most residential homes, certainly most new construction homes. Okay. There's something called a gravity wall furnace that doesn't have a fan. That's not a central. So, a wall furnace, there's flame happening inside of a heat exchanger, and the air is just naturally convecting past that by gravity. Hot air rises, cold air falls. Okay. Um, there's old floor furnaces in houses, work kind of basically the same way. All right. So those are gravity furnaces. You can have a wall furnace that does have a fan in it. That just pushes the air, makes it a little better. Oops, excuse me. That was my reminder to take a break. We'll get past this section. We'll take a 5 or 10 minute break here in a sec. Old floor furnaces, I mentioned those. Very old, old fashioned, very dangerous, by the way. They're getting old. Those heat exchangers crack. Room furnaces is just a much smaller version of a wall furnace. I remember my grandmother had little propane heaters in her bathroom, and I would always throw little pieces of toilet paper into it. Stupid, stupid. All right, electric resistance, that's much more common, and it can be in the form of baseboard heating. You'll see those little baseboards. You can turn the knob and you hear it, and it starts smelling funny. Old baseboard heaters. You can have electric resistance central furnaces. Okay, so electric resistance is just creating heat directly from electricity by converting electricity directly to heat. A large current takes a lot of electricity to do it. A little coil heats up. Blow dryers are electric resistance. The little plug-in fans are electric resistance, or the plug-in heaters. I mean, even the what they call the plug-in oil heater. It's an electric resistance element, but it's heating an oil inside this. Looks like a radiator kind of thing. Still electric resistance. Central heaters, baseboard heaters, radiant heaters, water heaters, a lot of electric resistance water heaters, wall heaters, etc. Very common. Not as efficient. It's efficient in the sense that it's very good at turning electricity into heat, but electricity is expensive. And so even though it's 100% efficient, because electricity is expensive, it's still a very expensive form of heat, electric resistance heating. Heat pumps, on the other hand, are very, very clever. Heat pumps use electricity, but they don't create heat from the electricity. They move heat. They condense it in a colder area and they bring it to a warmer area and heat up that space. Okay, so they can actually extract heat from very cold outside air, extract BTUs from the cold outside air, condense it, bring it in the house, and dump it inside the house and actually heat a house that's much warmer than the outside air. Okay, as it turns out, it takes a lot less electricity to do that than it does to create heat, like electric resistance does. About 1/3 is less. Okay, so now, technically speaking, heat pumps are 300% efficient because it takes 1/3 as much electricity to move heat as it does to create it, like electric resistance heat does. That's why heat pumps are now competitive with gas furnaces in terms of cost. Okay. All right. Hot water systems. There are space heating systems that use hot water. We call that a hydronic system. Okay. Let me go to this next diagram here. So you got a hot water coming out of your water heater, and cold water comes in, hot water comes out. This is what we call a combined hydronic system. This water heater provides domestic hot water for showers and washing and stuff like that, but it also heats the space. Okay. So hot water goes to the house, but we steal a little bit of that hot water and we blow it through um, basically a fan. Okay, we blow it through a coil. We run hot water through the coil. We blow air through that coil, and it heats the air, and we can distribute it to the house. Very common in apartments and things like that. Combined hydronic, forced air hydronic. Okay, but there's a little pump is stealing water and it cools it off a little bit. It blows it through there, it heats the air and cools it off, and then that warm water comes back and goes into the water heater. Now, this water heater has to be sized to handle the space heating load, but also size the domestic hot water demands. How many showers are people taking and stuff like that? So that's a little complicated to design those systems. Or you can have a dedicated water heater, and when it's a dedicated water heater specifically for space heating, we tend to call that a boiler. So when you hear someone say boiler, that's usually a water heater that provides space heating. Okay, but there's also boilers that do everything, and it depends on how hot the water gets and things like that too. So it's not exactly definitive definition of a boiler. So here's what it. So here, go back to this diagram here. So you got hot water coming out, warm water coming back for a combined hydronic. Here you've got a boiler. You got hot water coming out, warm water coming back. What's happening over here? This guy. So hot water's coming in, it's running through a coil, looks like a radiator in your car, okay? And then a fan is blowing air across that coil that has the hot water in it, and it's heating up the air. And then that air is blown into the house. So hot water in, warm water out, because we've taken BTUs. We've cooled the water with the air, which warms the air. So it's a transfer of BTUs. Remember, BTUs per hour. Another interesting type of heating system is radiant floors. Radiant floors. They're usually a heating only system. They're usually most popular in areas that don't require cooling, because as soon as you require cooling, you have to put in a duct system for your cooling. If you're gonna have that, you may as well put heating in your duct system too, and then it kind of makes the floor heating not as good. Or so basically, only people who can afford both will put in both. Or radiant floors are very popular where there's not much cooling, like in Tahoe or on the coast and stuff like that. Really, really nice form of heating because there's no moving air, so there's no drafts or anything like that. So it's basically your floor gets warm, and that heat radiates up. But it's based on hot water, so you need hot water coming in, and you get warm water coming out. So that's where your boiler or your combined hydronic water heater can hook right up to that. Here's what one looks like before they pour the concrete over it. All right. Okay, let's take a 5-minute break. I showed 10:06. Let's reconvene at 10:11. So take a bio break or refill your coffee, do whatever you need to do, stretch. I'm going to stretch. Ugh, ugh. We'll be back at 10:11. 10:11. All right. Okay, I'm back. Welcome back, everyone. All right, slap your face, throw water in your face, wake up, wake up, do calisthenics. We got to get going here. I am right almost exactly halfway through my slides, which is amazing. I'm almost always behind, so I think we're doing okay. I'm going to pick up the pace just a little bit to leave us a little time at the end for questions and answers and for a little survey that Itza would like to do about the class. So, all right, here we go. There are many varieties of residential HVAC configurations, okay, around out west. We're primarily talking about west. And I deal with HVAC contractors all over the country. And trust me, there's some pretty interesting stuff out there. There's places in the country where they only put their HVAC in basements. And I'm like, I'm from California. I don't even know what a basement is. I've heard of them. Is that like a wine cellar? you know? Yeah, basements, sheet metal ducts. Wow, we do all flex duct out here. But the popularity on the type of system depends on a couple of things. Usually, the first thing that determines the configuration of an HVAC system is the architecture. What is the house like? Is it a one-story house, two-story house? Is it a raised floor house with a crawl space? Is it a slab on grade house? Is it a multi-level house? Does it have an attic? All those things come into play when an HVAC contractor comes and looks at it and starts designing the system. They're like, okay, where can I put the air handler? Where can I run the ducts? Where can I put those supply registers? Where can I put the return grills? That all comes into play to determine the configuration of a system. You obviously cannot run ducts in a crawl space if there's no crawl space. All right. Like a slab on grade house. So a slab on grade house, now there's exceptions to everything. There are ducts designed for under slab use. And they're sort of popular in the Palm Springs area, believe it or not. It's basically a big PVC pipe that they bury in the ground and they pour the slab on top of it. And you got these big plastic tubes coming up through the slab, and that's their ducting. The problem is it's a giant P trap if water collects in it if they don't seal those ducts very well, and they have to be plastic. I've seen people try it with metal and they 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 rust right away. So, anyways, there's exceptions to everything, but the most common types of systems or the most common kinds of homes I see in most of California is a slab on grade house, which usually means you got to put your ducts up in the attic. Okay. But there are raised floor houses, especially on the coast when you got sloped terrain. You'll build a raised floor house, and then you put the ducts underneath the crawl space with the registers in the floor. So let's look at all the different configurations. Um, the other thing is cost of installation and how easy is it in a retrofit situation. If let's say someone has only baseboard heating in their house and they want to convert to central forced air heating and air, um, then you're really limited because it's very difficult to open up walls and sheetrock and stuff like that to do that. But let's say that you have an older single story home that has a very adequate crawl space as well as a very big attic to work with. Okay, one story house. In deciding whether to put in an upflow unit and run the supply ducts in the attic or a downflow unit and run the supply ducts through the crawl space, get bids for both. Get bids for both. Also, it kind of depends on whether it's a heating or cooling climate, too. Okay, we'll talk a little bit more about that. Before we describe the various configurations, we should probably talk about the different parts of a system. Okay. The generic system that is most common in our area and in our part of the country is a forced air ducted central system. Okay. You're starting to see a lot of ductless mini splits go in it, but those are kind of special applications. Okay. Most normal size, bigger houses will have a central forced air ducted system. Forced air means there's a fan. Ducted means there's ducts that and supply registers going out to the rooms. And central means there's just one or two big units serving the entire house. Okay. Depending on the size of the house. The systems are most commonly gas furnaces, but now there's a big push to switch over to heat pumps. All right. And then the type of ducting is most common what we call flex duct. The correct term is vinyl helical flex duct. Okay, and it's just a flexible duct. It's a plastic tube that we blow air in. It's very flexible, and then we use sheet metal fittings to split it into different parts and pieces and stuff like that. You might see in some older homes some rigid metal ducts. Okay. There's places in the country where they absolutely despise flex duct. they think it's the they think it's the bane of civilization. And I'm constantly arguing with them. But anyways, um, sheet metal duct can be round or rigid. They also make rigid duct out of something called duct board. Okay. So let's look at some configurations that are most common in our area. So here we have one. So here's this lower diagram is a slice through the house. So we're looking at the house from the side, and there's a slice through the house, and we're looking at that slice. And then the top one is looking down on top of the roof of the house. Okay. And maybe the roof is transparent so we can see the ducts underneath it. So here is a package unit on the roof with all the ducts in the attic. Okay. So here's the package unit. The ducts run around. It's all flex duct, sheet metal TYs, these little Y-shaped fittings here. These are all supply registers or register boots. And the registers where the air is coming out, those are the supply registers. The air is blowing into the space. And then you'll usually see one or two big registers with an arrow going into it. That's the return. So an HVAC system is a cycle. It's a loop. Air gets pulled into the return, usually filtered at the return, goes through the return duct, goes into the heating or cooling system where it's heated or cooled, and then it goes through the supply ducts and comes out the supply registers and then passes through the house and it does it again. And it's a big loop, it's a big circle. It keeps going around and around. Okay. Here is an upflow unit. So the air is blowing up, all the ducts are in the attic, all the supply registers are in the ceiling. The return grill is down low. You'll see those. This is usually a furnace in a closet. It can be a furnace in a garage. Okay. Here, this is very common in new construction. I've designed thousands of these. Okay. Thousands and thousands of these. Um, horizontal unit, horizontal furnace in an attic with all your ducts in the attic and all your registers in the ceiling. So you'll have one or two big return grills. The air gets pulled in, heated or cooled, and then blows out. Okay. Here's kind of what it looks like from above. Very, very common in new construction. Um, this is this is not what I live in now. The house I live in now is a downflow. I think I have a diagram of that. This is a package unit. Remember I said package units can sit on the ground, and if you have a crawl space, you can run the ducts through the crawl space. This is very typical. Do not allow the ducts to lay on the ground like this shows. That's a bad installation, but it's quite common. Okay. But here all your registers are in the floor. Your floor registers and your return is in the floor as well. So that's a ducted unit sitting on the ground with all the ducts in a crawl space. Here's what I have in my house right now. It's a downflow unit. Okay. Our furnace is in a closet. The air blows down. All the ducts are in the crawl space, and all our floor registers. I was pointing up to the ceiling earlier. I was lying to you. My floor registers are actually on the floor. My supply register in the floor. But you can also put a horizontal unit underneath the house if you've got plenty of room. Sometimes you'll see this if a house is built on a slope and the crawl space is really tall on one end or one side. You can actually hang a horizontal unit in the crawl space and have everything there. So that's fairly common too. But I would say most common for houses built in the last 20 or so years is the horizontal in the attic. Okay. But there's exceptions to everything and depends on a lot of things. What if you have a two-story house? Well, you might have to do a combination of things. You could put a horizontal unit in the attic. You can put a downflow unit on the first floor with a crawl space. But what if the first floor is slab on grade? You can't do that. You could put an upflow on the first floor. You'll see these in garages. You'll see a furnace in the garage and then a unit upstairs. That's only if the system needs two systems. Okay. That's better in terms of control, but it's more expensive to put in two systems. What if it's a small house that could be easily handled by a single system, but you got two floors? Well, then you got to figure out where to run all the ducts. Again, I've designed many, many of these. I've designed thousands of homes, and probably 2/3 of them were two-story homes. And you put a horizontal unit in the attic. All your second floor registers are in the ceiling, but then you got to find a way to get the ducts down to the first floor through what we call chases. And that's just a boxed out corner somewhere in the house, like a closet or something, to run a duct down? And then where does it hit on the first floor? Can you run it through the floor joist to get it to the registers? Very, very challenging. Okay, for the architects in the room, think about that when you design a house. Put the chases so that they line up with where you want the registers to go. I can't tell you how much of my early career was begging architects for chases. Please, please let me box out this corner of the closet. Please, please. No, that closet's very expensive. That's valuable square footage, but I got to get ducts to the first floor. That's a summary of a dramatic reenactment of my career. All right, configurations of two-story homes. All right, now the new things you're starting to see a lot of are mini splits. Mini splits. Split means it's a split system. So there's an outdoor condenser and an indoor air handler. Okay. These have been around for a long time in Japan. But in the last 15 or so years, they've become super popular in the United States. And in the last few years, their popularity has just skyrocketed. Okay. Because we want to switch to electric heating. We want to get away from carbon producing gases. We want to, and that's all well and good. I'm 100% for all that. But for me, there is no comparison for safety. There is no comparison for safety. The fact that we pipe explosive gas into our homes, and then when we use that gas, it becomes poisonous gas, and you read about it all the time. People die every single year from gas heating, and that's good enough reason for me. But there's a lot of other reasons too. There's the whole fact that our grid is slowly becoming more green. You can run heat pumps off of the solar panels in your house. All this other stuff. I won't go into the details of that, but it's the technology's come a long ways, and there's really good reasons to do it. There are some disadvantages. Okay, I have a whole class on heat pumps if you want to learn about the advantages and disadvantages of heat pumps. But today we're just talking about like how to identify them. Okay, so mini splits. I mentioned earlier, one of the cool things about mini splits is they're small. They're little tiny things. They're so cute, little half-ton little dudes and 3/4 tons and 1 tons, which is a much better match for the small dwelling units that we're building these days. Like I said, back in the day, if you built a really small house, the smallest air conditioner you could buy was 1.5 tons, and that was way, way bigger than what we needed. And so people would sometimes they just put window units on it or something like that. But now it's much better, much better. Mini splits, most people think of ductless mini splits. Okay. They do make a ducted mini split. The outdoor unit is exactly the same. On a ductless mini split, it's usually the wall mounted unit or the ceiling cassettes. Okay. But a ducted unit is a little air handler that'll mount in a drop ceiling, and it's got a return duct coming in one side and supply ducts coming out the other side. I don't have a good picture, unfortunately, in this slide deck. So ducted and ductless mini splits. Most people, when you say mini split, most people are talking about ductless, but just know that ducted. I personally prefer ducted. Ducted. They distribute the air much better. These are true split systems. The condenser's outside, the air handler's inside. The ductless version come in the wall mounted or cassettes. Condenser is the condenser. The outside unit is what we call a suitcase condenser. Okay, it's shaped like a big suitcase, and the fan blows horizontal, as opposed to the old style that we showed earlier, where we get the model numbers off the air conditioning condenser, the big box with the fan in the top that blows air straight up. That's the older style. The new ones are smaller and they're horizontal airflow on the condenser. Here's a picture of the outdoor unit. Okay, suitcase or briefcase. Sometimes people call them briefcase condensers. Very nice, compact. Here is the a wall-mounted unit, and I meant to find some better pictures of a cassette unit, but I couldn't. Sorry, ran out of time. And then the ducted ones can be in what's called a soffit mounted coil. Some we used to call them pancake units because they're fairly flat and they'll fit in a 12-inch drop ceiling. Very popular in apartments. I've designed many apartments that had these. They're accessed through a panel in the ceiling. You'll see these in larger hotel rooms. You'll walk in and there'll be this metal thing with screws in it, and it looks like an access panel. And if you open that up, it goes right inside the air handler. Sometimes that's the actual return grill too. Okay, very common. This is kind of what they look like. So they mount in a drop ceiling. So here's the actual ceiling. There's a 12-inch drop ceiling, some sort of a soffit, a dead space above the ceiling that you see. Um, there's a box here, and it's got a fan in it, and it blows the air through the heating coil, maybe a cooling coil, a heating coil if it's a. This is what I was talking about, the hydronic. You can heat this with hot water, and then it blows out supply ducts, and you just run the supply ducts to the different rooms. Sometimes the return can be right in the bottom, so that you're actually seeing it. These are kind of noisy. If you've ever slept in a hotel that has one of these, you know it, because when that fan comes on, you're basically looking right up inside the air handler through the filter and seeing the fan. Okay. All right. Here's an interesting one. They're called high velocity systems, or also known as small duct high velocity, and all they really are is a really strong fan cramming air through little tiny ducts. Okay. And so when you cram a lot of air through a really tiny duct, the velocity goes up. So they call them high velocity systems. The nice thing about them is they're small ducts and you can run them through walls, and you don't need as much room to run them in the house. The trade-off is you're using a lot of fan energy to cram the air through little small ducts. Okay. And so there's a trade-off there. But the other trade-off is the ducts are small diameter, so there's less conduction. They're also pretty fancy how they connect them together, so they're usually very tight and they don't leak that much as well. Okay, these were designed for historical buildings, actually, running air through smaller ducts, so you didn't have to disturb the historical building when you're retrofitting it for central heating air, as opposed to the old floor furnace that used to be in those historical buildings. Very small diameter, 2 and 3 inch ducts. You can actually run it through a stud bay in a house. They carry enough air to heat or cool the room, but the air is moving really fast. Okay, it takes a very strong fan to overcome the resistance of doing that, and this fan energy is not cheap. Okay, very popular in some very new homes that have very complex architecture. A lot of the very modern style concrete slab houses with no attics and stuff like that. They're used for those as well. Okay, so just be aware that those are out there. All right, so let's go back to our more common system that we're talking about. Remember, I said in California, probably the most common type of system is a horizontal unit in the attic. Okay. But there's other kinds too. There's upflows and downflows and packages and stuff like that. We're just going to talk now about all the bits and pieces of that system, and those terminologies are fairly consistent regardless of the configuration. Okay, so let's talk about all the stuff. So this little diagram just shows everything. We're going to kind of go through each one of these in a little more detail. But let's start right here with the heart of the system. This is the air handler. This is the box with a fan in it that's pushing the air through the supply registers and pulling the air through the return. Okay. So the air is being pulled through here through the return grill and then pulled through the return duct. Okay. And then if we have multiple ducts coming in and there's a box that those ducts are connected to, we call that a plenum. So in this example, there's a return plenum. Again, it's just a box that you connect ducts to, is all it really is. Then it goes through the air handler, the big fan in there. And then if it's a furnace, it's going to have a separate coil. So it blows through the coil to cool it. If it's a heat pump, the air handler and the coil are all in the same box. So basically this line right here goes away. So the coil and the air handler is all inside the same box. Then it comes out. And if you want to connect the multiple ducts to it, you need a plenum. You need a box that you can attach ducts to. So now we have a supply plenum. And these little things here, it's basically a sheet metal box, sometimes a ductboard box. And the way you connect a round duct to a sheet metal box is you cut a hole in it and you put this collar in there that the duct can slip over. And it's called a start, START, start collar. It's where you start a duct off of a plenum. So there it is right there, start collar. There's other names for it, other parts of the country. It's interesting, all the terminology that different people use around the country. But this is fairly common, a start collar. Okay. And then if that air goes down the duct and it's a big duct, we call that a trunk if it splits. Any duct that splits into multiple ducts is called a trunk. If it's the last duct on the end and it goes to the register, we call that a branch. Okay. So trunks, branches, just like a tree, trunks and branches. So a trunk splits and a branch goes to the end. So how do we split a trunk? How do we split a big trunk into two smaller? It could be a branch and another trunk or two branches. Okay. We use something called a TY. Okay. If we're using flex, if we're using sheet metal, it's a little different. Okay. But it's TY. So you've got this flexible duct and you attach it to this fitting called a TY, which then splits into other ducts. And they make three-way TYs. They make all different kinds of TYs, but so TY is kind of a generic term. Okay. And then the duct goes to something called a supply register. But to connect the duct to the register, we need something called a supply boot. All right. Let's look at these in more detail. So here's what flex duct looks like. You've got an inner liner. This is the vinyl core, and it has a helical wire like a slinky. Okay, that's sandwiched between the vinyl side of the. There's two layers of vinyl sandwiched the wire, so that's what gives it its rigidity. So if you squish it, it poofs back up. It's fairly springy. Okay, it also allows 25 feet of duct to be compressed like a slinky and stuffed in a box that's only like 4 feet long. Okay, and then you pull this 25 feet of duct out of this 4 foot long box. Okay, um, it is by far the most common used from, I would say, from West Texas all the way to the coast. Everything is flex for the vast majority of systems. You go the other direction, and there's a lot more sheet metal. Okay, and I think that's primarily has to do is because the West has grown a lot lately. We have a lot more new construction going on. You know, Arizona, Las Vegas, all those areas are growing so fast. A lot more new construction and a lot more flex duct. Okay, let me just say this: a well-designed, well-installed flex duct system will work as well, if not better, than a sheet metal system. Okay. I will go out on a limb and say that, and I will defend that 100%. And I get in that argument almost on a daily basis. But I have people saying, I would never use flex duct. That stuff's garbage. It's not. If designed well, installed well, it's as good as sheet metal. In fact, I'm giving a big talk at a symposium, and I'm going to throw that out there to a bunch of people from Florida and see what they say. And I've got the numbers to back it up. So don't be biased against flex. Now, the one disadvantage to it is that too many amateurs try to install flex and they end up doing a horrible job and it looks terrible. And everyone goes, oh, it's because it's flex. No, it's because it was a horrible installation. All right. Well designed, well installed flex works at least as good as sheet metal. Okay. All right. So there you go, flex duct. Oh, and then sorry, there's the inner liner. That's what holds the air. That's what holds pressure, is that inner liner. And then right outside that is the insulation, which prevents conduction. And then the outside of that is what we call a vapor barrier. Out here, the vapor barrier is just to hold the insulation on the ducts. That's all it's good for. It is not supposed to hold the air. The air pressure is held by the inner liner. The insulation prevents heat conduction, and then the vapor barrier just holds the insulation in place. Back in Florida, Louisiana, Mississippi, the vapor barrier is to keep humid air from getting through the insulation and touching that inner liner, because then air condenses and then you get condensation on the bottom and your ducts start getting soggy. All right. But we don't have that problem out here in California. The next most common type of residential is round sheet metal, also known as KD pipe. You might hear somebody say KD pipe. Oh, that's all KD pipe, or I got to buy some KD pipe. KD stands for knocked down. And what that means is, in order to ship it easily, if they ship it in these round tubes, it's very bulky. But if they can take these round tubes and turn them into a U, they stack. So you take this stack of U-shaped tubes, and then you bring it over and you snip it together, and now it makes a duct. It makes a tube, and that's what this seam is right here. Okay. But then you also have to wrap it with insulation. Oh, and you have to seal all the seams or they leak really bad. Okay. So very expensive and not much benefit, if any, for all that extra cost in terms of airflow compared to flex duct. Okay. The real number one advantage of sheet metal that I cannot argue with is it's less susceptible to varmints. So what do? Keep the varmints out of your attic. Okay. And I know that's not always possible, but yes, in fact, I have had possums in my ducts under the crawl space in my house. So that is the one disadvantage of Flex is it more susceptible to critters. Other than that, I think Flex is superior in every way. Some people say, "Oh, it doesn't last as long as sheet metal." Baloney. I've seen sheet metal rust out in 8 or 9 years. Okay, Flex doesn't rust. Okay, all right, I'll get off my high horse. The next thing is the air handler. That's the big box. That's the box that has the fan in it. A furnace is an air handler, but if it's a heat pump, the air handler is what's called a fan coil unit. It has a fan and the coil all in one box. A furnace is going to have the fan and the heat exchanger, and then the coils on the outside of that. So here's the air handler. Supply ducts, I talked about that. That's the ducts where the heated and cooled air is coming out. Now, the thing to realize about supply ducts is there's a big delta T between the inside of the ducts and the outside of the ducts. So where the supply ducts are located is very important. If they're in an attic and it gets very hot where you are, your attic can get up to 120 degrees very easily, and you're trying to blow 50-degree cool air through those ducts, that can be an issue. Okay, there's going to be a lot of heat transfer there. But if you can bring your ducts inside conditioned space, way to go. Then you basically don't have any heat transfer. Your ducts are in the space in which they're going to be heating and cooling. So that's good. Okay. Um, supply ducts are under a positive pressure. The fan is pushing air through those ducts, and there's resistance. So everywhere along the way, the air, if there's a leak, air wants to come out of a supply register. All right. So here's our supply trunks and supply branches. Those are all supply ducts. Return ducts, the air is being pulled through. Okay. And if there's a hole in a return duct, air is going to be sucked in. So when you have leaks in the return ducts in your attic, it's pulling very hot air into those ducts as well as dust and pollutants. Okay. So return leaks are bad. The delta T isn't as big of a deal on return ducts because the air is just being pulled out of the house. It's the air theoretically is the same temperature as the house, which is much less than air that's just been heated by your air conditioner or air that's just been heated by your heater and cooled by your air conditioner. Okay, so the delta T is not as big of a deal on return ducts, but leaks can be a big deal on return ducts. So there's our return duct. Here's one, and here's one over here too. TY, I mentioned TYs. It's a sheet metal fitting, and all it does is it takes one big duct and splits it into two smaller ducts. That's it. Okay. They do make three-way TYs. So you have another one coming off over here. But this is very common how you look. Notice that one of the ducts usually goes straight through like this, and one of the ducts comes off at an angle. When we talk about duct design, we talk about something called equivalent lengths, which is a way to quantify resistance to airflow or friction. And the air blowing straight through here has much lower equivalent length than the air that's being pulled off and turned and has to go this direction. Okay. They make a kind of TY where they're equal instead of one favoring the other direction. But anyways, TY is a fairly generic term. A lot of different kinds of TYs. And then there's something instead of a TY, they make these ductboard wedges. We call them cheeseheads sometimes, or ductboard boxes, triangular wedges, and my dog's tail's knocking on my door. It sounds like somebody knocking. And these are kind of interesting. These don't move air nearly as well. There's a lot more resistance to airflow through these, but they have some other advantages, and that is that one of the big challenges with installing duct system is all the different kinds of parts you need. You might need 10 or 12 different kinds of TYs. Well, these are interesting because you only need 2 or 3 sizes of these boxes, and then you bring the start collars that you need, and you basically build your own. They're like a field fabricated TY, and so there is some savings in that regard. But these are duct board, which is fairly fragile. It's like if you took fiberglass bat and you smashed it and sprayed it with glue and let it harden. Um, It's about as rigid as styrofoam, like what you would make an ice chest out of, and it's about that fragile too. It's easily broken. So if you put these up in your attic, you want to make sure no one steps on it and stuff like that, or they don't get beat up when you're installing it. Okay, but they can work. They can work just fine, but you have to account for the extra friction, so that you might have to have bigger ducts to accommodate this friction to get the same amount of airflow from a duct system that has sheet metal T-wise. Okay. Uh, Register boots is how you get a round duct and connect it to a rectangular register. Okay. So look in your ceiling, find your ceiling register, or look at your floors, find your floor registers. And if you were to lift that floor register out and look down in there, there's gonna be a box. And then that box is going to have a round duct probably connected to it. That box is called the boot, the register boot. And it needs to be airtight. It needs to be well sealed. If it's a ceiling register, it needs to be well sealed to the sheetrock so air doesn't leak up into your attic. And if it's in the floor, it needs to be well sealed to your floor so air doesn't go back down into your crawl space. If you have floor registers, it's fun because you can just lift the register out and look inside, and you'll see that sheet metal box, the bare edge of the sheet metal. If you can see a gap around there, air is going to leak back out of that gap. And so what people will do is they'll take foil tape and they'll bend it around the edge and seal that up, or they'll use a mastic or something like that. But that's register boot. That's what we're talking about, is this box right here. A chase, I mentioned chases in two-story houses. A chase is just a boxed out section that you can get a duct from the attic down to the first floor. Okay. And it's a chase. Okay. So here's a chase right here. Here's a chase right here. Here's a chase right here. So you see all these ducts come off this supply plenum up in the attic, go down the chase, and then where do they go is a lot of fun. You got to get them through the floor joists or a drop ceiling, or you got to avoid beams and all this other crazy stuff. If you're gonna design HVAC systems for two-story houses, you're gonna have to learn to read structural plans really well. You're gonna come to hate flush beams and stuff like that. Okay. Start collar, I mentioned those. That's how you attach a round duct to a box. So you got this box, that's our plenum, and we need to attach a round duct to it. So we cut a round hole, and this collar fits in, and it's got these little tabs that bend back around that, and that's what holds it in place. And these leak really bad if you don't seal them, because those little tabs bend back, and if you don't cut that hole exactly right, which they never ever do, that leaks really bad. So right in here leaks really bad. So we have to seal that. And the best way to seal it is with mastic, which is, it's like pancake batter. It comes in a bucket and you apply it with a paintbrush, and that seals up all those holes, and you put tape and other stuff over the top of it. Okay. But a start to collar is what we're talking about. I already mentioned that. And then another type of fitting is a squared around. A register boot is basically a squared around fitting. Okay. But sometimes you may go from a round duct to a square duct. And so you got a round duct and it just turns to square, and then you connect it. Those are very common. Sometimes they'll drop a duct down in a chase. We call that a wall can. Okay. But a squared around fitting just takes a square duct, converts it to a round duct, or vice versa. A wall can is a duct that fits inside a wall. So if you have a 2x4 wall and the 2x4s are 16-inch on center, that leaves about 14 inches by 3.5 inches of a wall cavity, the stud bay. Okay. So it's 3.5 by 14. So they usually will use a 3x14 can and fit it right inside that wall. You got to cut out the top plate to get that duct down into that stud cavity. Structural engineers hate when you cut through their top plates, but it is done occasionally. I'm not a big fan of it. There's a lot of resistance there. There's a lot of problems. I would just as soon put a register in the ceiling right here. Okay. And the book, by the way, we don't have time in this class, but the book goes into a lot of talk about where to put registers and things like that. Okay. Well, condenser, we talked about condenser. It's the big outdoor unit. Okay. And in cooling mode, this is extracting heat from the inside of the house, and it's squeezing the heat out of it and dumping the heat to outside. So here's those refrigerant lines I was telling you about. One is the size of your thumb, one is the size of your pinky. The big one has a hot gas in it. Actually it's a cold gas, but it's all relative. It's coming in and it takes this gas and it squeezes it back into a liquid. It extracts all that heat and the heat comes out. And if your air conditioner is running and you go outside and you put your hand over this air conditioner while it's running, that air is warmer than the outside air that's being pulled in the side, which means BTUs are being added to it. Those are the BTUs that used to be inside the house because the refrigerant expanded inside the house, absorbed those BTUs, goes outside, they're squeezed out, and they go out to the outside. That's what the condenser does. And a heat pump, the condenser looks just like this, but there's a little valve that switches direction. And then in the wintertime, it does the opposite. It extracts heat from the cold outside air, sends it inside where it's dumped. Okay. The coil, this is what the indoor air blows across this coil. This panel is removed. And this is where the liquid refrigerant comes in and expands and gets cold, and the air blows across it and cools the air. Sometimes called evaporative coil. There's a little thing on here called a TXV. You might hear of a TXV. It's just a way to control the volume of gas that's going through this unit, makes it more efficient. Thermostatic expansion valve. Okay, there's different kinds of coils. This is an A coil for obvious reasons. It's shaped like an A. Oops. Here's an A coil. They also make U coils. They make W coils and they make slab coils. Okay. It's all just different ways to fit it into a different size box. Okay. A coils are probably the most common. Here's a TXV. Fairly complicated topic for this class, but just know that a TXV regulates it senses the temperature of the outgoing refrigerant and adjusts the rate of the incoming refrigerant to make the air conditioner work more efficiently. Okay. Here's what it looks like. You see this little spaceship on top of here. One that does not, let me go back a couple of slides. This does not have a TXV on it. This is just called a straight orifice. You see, there's a pinhole inside here. The liquid refrigerant comes in here and goes through here and then expands, turns into a gas. This is a non-TXV unit. And then here's what a TXV looks like. Pretty obvious when you see the TXV. It's right there in front of you. And then this is the sensing bulb. Comes out. You can see this little metal cylinder there. Oops. Sorry, that's my warning that I'm running out of time. Okay, I need to pick up the pace. Refrigerant lines. One's as big as your thumb, one's as big as your pinky. It's important that they system be properly charged. That's been a big problem, is that they're not charging equipment very well. There's a little bit of a technical issue. I mentioned plenums. That's the box that you attach ducts to. Supply registers is where the air comes out. A lot of different kinds of registers, some very, very good registers and not so good registers. The book covers a lot about what's good and what's not so good. Here's a little quiz. What's better for heating a room? What's better for heating a room? Floor registers or ceiling registers? Okay. Floor, that hot air is coming out, blowing up. Ceiling, the hot air is blowing down. So what's better for heating, a floor register or ceiling register? Most people will say floor registers. And you say, why? Well, heat rises. So let the air come out, let it come up. That works better. It's actually not true. It's not the case. Ceiling registers are better for heating because they blow the air down. The air doesn't want to go down. The air wants to rise up. So if the air comes out of the floor register and rises up, where's it going to do? It's going to stay at the ceiling. Hot air is going to rise and stay there. But if you blow it down, it's going to go blow down. It's going to mix, and then it'll slowly rise up. But by that time, it's mixed with the room, and you get better mixing. Registers are all about mixing, 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 mixing. Okay, and then here's just a diagram for that. Air comes out, blows up, stays up. If you blow the air down, oops, wrong direction. If you blow the air down, it gets down to the floor where you want it, and it mixes, and it's less likely to rise. Now, the opposite is true for floor registers. Or sorry, for air conditioning. For air conditioning, floor registers are better Because if you have ceiling registers, you blow the air down and it's cold, it wants to stay down on the floor. But if you blow it up, it goes up, hits the ceiling, and you get better mixing. So my general rule of thumb for registers is blow the air the opposite direction that it wants to go. If it wants to rise, blow it down. If it wants to fall, blow it up. If it wants to go out the door, blow it away from the door. Okay. So, and then, but the problem is you don't have different registers for heating and different for cooling. So you got to pick one or the other and hope for the best for whichever one it's not working for. Again, it's all about mixing. Okay. Register types. There's a lot of different types of registers. I have my preference where I like to put stuff, and I have reasons for that. But you can put a register pretty much anywhere in the room and get it to work okay, if as long as you use the right kind of register, as long as you have good airflow. And here's the other thing that people don't think about: as long as your equipment is not oversized. If your equipment is oversized, the air conditioner runs on much shorter cycles. Okay, and it doesn't run long enough to mix. Okay, so very, very important. Load calculations and equipment sizing has a lot to do with how well a register will work in a house. Okay, how well that air mixes. Okay, different kinds of registers. There's bar type, straight blade, bar type, curved blade down here, and then the middle something. Sorry, stamp faced straight blade, stamp faced curved blade, and then bar type in the middle. Bar types are much, much better. They have much better airflow. Bar type, BAR, bar type. All right, I'm going to skip all this. We kind of covered some of this stuff here. Basic thermodynamics, talk a little bit about refrigerant cycle. I'm sorry, I totally ran out of time, as I usually do. I was doing so good at the beginning of the class. You'll get copies of these slides, by the way. This shows the refrigerant being condensed and etc. This is kind of a technical topic. And that's it. I really appreciate you guys. Itzel, if you would like to cover your slides there.
Yeah, I'll just take a really quick moment. While I talk about the slide, I'm going to launch a poll that is just for you all to let us know how we did today and if you enjoyed the class. Very quickly, if you're seeking learning units, we have AIA and ICC learning units. Feel free to email me. Just put my email in the chat if you have any questions about that. Um, we'll also be sending the slides and the recording to you by end of week, so be on the lookout for that in an email. And just some upcoming courses that we have coming up in the month of February. If you want to take a deeper look into those, I'm also putting our calendar link in there. Feel free to register for anything that looks interesting. And I think with that, that's it for me. I'll hand it back to you, Russ, for
Sure.
any questions. Okay, we also have, I forgot about the slide. Just another shout out for our energy code coaches. If you need any sort of, if you have any sort of questions about Title 24, we have our energy code coach service. We have a number, and you could also fill in an inquiry form on our website, and they'll get back to you fairly quickly. So it's a great, great tool.
I think there's one more slide. Oh, that's it.
Yeah.
I did see a question that I missed. Julie asked, it says, traditionally we place a ceiling or top of wall register above a window. I've heard that's not considered so important anymore. Is that correct? Correct. You can put a register over a window. The book, by the way, has what we call the 4 schools of thought. Also, my blog. I have a HVAC blog. It's russellking.me, RUSSELL king.me, and I cover all this stuff. So like I said, if you imagine a bedroom and the window's on the other side of the room, if you put the register above the window, the air is going to come out, it's going to heat and cool that side of the house, and it's going to go through the room and it's going to leave. You don't get as good of mixing if you do it that way. If you put it if you put the register back interior to the room and make it a directional register blowing across the room towards the window, remember, blow the air the opposite direction that it wants to go. The air wants to go out the door. So if you put the register close to the door, blowing away from the door, it has to collide with that air that's trying to leave, and you get much better mixing. But then you have to think of things. There's something called throw distance to make sure that the air gets at least close to the window, so you don't have stagnant areas and stuff like that. So it takes a little more thought to design it that way, but it actually, in the long run, it works better because you have a shorter duct instead of running it all the way out to the window. There's that much less duct work, so you get better airflow and less conductive heat losses, and you get better mixing. Okay, but you can make it work by putting the register over the window, but you have to make sure you have the right kind of register. You have to make sure you have good sized equipment with nice long run cycles and stuff like that too. So a lot of that stuff comes into play. So yeah, good stuff. Awesome. Oh, Julie's asking, so top of wall is better than ceiling? If you can get a high sidewall register, that's actually my preference. The problem is how do you get the register to that sidewall? If you have to drop a can down and then blow it across, you lose a lot of friction, or you have a lot of friction and you lose a lot of airflow by dropping a can to get that high sidewall register. But if the room next door has a lower ceiling, or you can drop a ceiling like in a closet and then come straight into the back of that sidewall register and blow across the room, and then use a bar type register. That actually is one of the best ways to do it, because then you're shooting that air straight across the ceiling. It has a nice long throw distance and has good airflow properties, and it gets all the way to the other side of the room, and it mixes really well. Okay. So it just depends. It just depends. Awesome. Thanks, everybody. All right. Did everybody take your poll?
Mhm. I closed it off a little bit ago.
Okay.
Thank you for
Awesome. All right. Well, thank you. So appreciate it.
All righty. Have a great day, everyone. Bye.
See you later.